Hi, this is the second class of Semiconductor Engineering 2, and I'm gonna tell you about the MOSCAP. MOS, first of all, we have to know what is MOS. MOS is the simple word of metal oxide semiconductor. And here's the metal part, and this part is the semiconductor part. And the between of the metal and the semiconductor, we use oxide on it. And this is the simple picture of the MOS. And we say the metal part gate and oxide part. There's are several words, the gate oxide or gate insulator or gate dielectric. And the semiconductor part, we say this part body. And so we can say this GOS, so gate, oxide, and semiconductor. So this is the very simple metal oxide semiconductors picture. And I'm gonna tell you about how to draw MOS energy band diagram. So let's start with metals metals energy band diagram. So we say metal and we suppose two things. First things is the there's there's our free electrons, and the second thing we suppose equal equal potential. The word equal potential means that the every part of the metal has the same potential on it. So when we have a bias, when we goes or bias on a metal, the band doesn't bending. So we suppose two things. But in this energy band diagram, we will not use metal. We will use semiconductor, especially we can use p-type or n-type, but in this energy band diagram, I will use n-type semiconductor. And there could be some question why we use n-type semiconductor. But however, we don't use the general n-type semiconductor, we use heavily doped n-type semiconductor. So as I as I tell mentioned bef as I tell you before, the n-type semiconductors energy band diagrams are like this, and these parts are conduction band, and this the lowest part is the valence band. And in general, n-type semiconductor, the Fermi level is near to the conduction band, but we suppose that this n-type semiconductor are heavily doped, so the Fermi levels are almost near to the conduction band. So this is like Fermi level. So this is the metal part, and we can say this not just n-type semiconductor. We say this n plus semiconductor. So this is the left part of the metal oxide semiconductor. So this part are the gate. I'm drawing the gate energy band diagram. So let's draw all things of the mass. So mm, we can draw like this. This is the, as I mentioned before, the M plus thing, and this is the gate. And this is the oxide part and conduction band, valence band. As you can see it, the conduction band and the valence band, the band gap is very high. So because this is the dielectric, or we can say insulator, we use silicon dioxide material on it usually, and the right part, the semiconductor parts, we use a P-type semiconductor. So P-type semiconductors Fermi levels are near to the valence band. So I can draw like this. And the half of the band gap is the intrinsic Fermi level. I can draw like this. This is the energy band diagram of the mass before we junction it. So this is the three part of the mass. So let's junction it. So the easily way to draw the energy band diagram of metal oxide semiconductor in summer equilibrium condition, the as I mentioned before, the first class of the semiconductor engineering, how to draw p-n junction, that in summer equilibrium condition, we draw the Fermi level constant first, and this is the same. We have to draw the Fermi level constant first because when there are gradient on Fermi level, that's mean there are difference of carrier concentration, and when there are difference on carrier concentration, it means there will happen diffusion current, and that's mean there are now current flowing now, and when when the semiconductors are in summer equilibrium, there should not be current flowing, so it doesn't make sense. So we have to draw Fermi level constant first. So I can draw like this. And the poly semiconductor, the gate part, will like almost same of the conduction band and the Fermi level. So this part is Fermi level, and this is the valence band. And and before we draw the oxide part, we can say the right part of the semiconductor, the body part. So this was the P-type semiconductor. So we can draw like this. And we can draw the oxide part here now. And the difference of the conduction band between the oxide and the gate is the band offset. And the band offset is should be maintained when we junction it because the band offset is the material property. It doesn't matter with the junction or the bias. So the difference of the conduction band between the oxide and the gates should be maintained. And also the part of the gate oxide and the body part of the difference of the conduction band and the valence band should be also maintained because it is material property. So it bends like this. I should draw again because this picture was not great. So mm, mm, it bends like this, and the part are 1, 2, 3 like this. So this part are the band offset. So this should be maintained. And we have the Fermi level constant on it. So this part are the gate, and this part are the oxide, and this part is the body. Or we say this part substrate. There are several words we can say on it. So this is the metal oxide semiconductor. Actually, we don't use metal on it, so we can say this part gate. So GOS is the words we can say on it. So yes, this is the mass mass energy band diagram. In similar equilibrium condition. Yes. So the next class will be the how the energy band diagrams gonna change when we have a reverse bias or forward bias or the some things on this part. This part is we say surface. So what's gonna happen on the surface or how's the energy band diagram change when we have a forward bias or reverse bias. So thanks to watching my video and I will gonna have a video next week. Thanks.